So good morning, everyone. I'm very grateful and honored that you're there because it's 8 a.m. Congratulations. So I wanted to talk about the usual thing I do, which is extracting connectome biomarkers with machine learning. But then the others kind of told me I had to be a bit more provocative and answer the real question of the workshop, which is how do predictive connectivity models meet the clinician needs. So I thought I would take a strong statement just to stir up the discussion. And I'll claim that I believe that predictive biomarkers are today the most useful endeavor for clinical applications of functional connectivity. That's a strong statement. I'll also claim that they are currently not reliable enough. So my presentation will have two aspects. In the first part, I'd like to stress my point that prediction really matters. And then the second part, I'd like to show you how we do it these days and what are our conclusions on the best ways of doing it. And so the point I'll try to drive through during the first part is that machine learning is useful and that it must be done right. And of course, that slide may be a bit difficult to come up. Oops. There we go. Yeah, it was hard to come up. So yeah, when I discussed with my colleagues, they tell me, prediction? Nah, we want biological insights. But what if I told you that brain imaging predicts the risk that a 2-year-old develops on the autism spectrum? It's not currently the case, but what if we could do this? What if we could have brain imaging predicting long-term cognitive deficit after stroke? Would this be interesting for the clinicians? We can discuss this afterwards. I believe so. Big pictures slow the presentation, and I don't remember what's the next slide. There we go. Okay, so is heterogeneity a roadblock? That's the first thing I hear, that we won't succeed in this endeavor because there's heterogeneity. So we looked at autism, which is a difficult pathology to work with because it's ill-defined from a diagnostic criteria and it's very sensitive to the parent's socioeconomical status. And so we looked at ABIDE, which is a post-hoc aggregation of data across many sites in many countries. So it's terribly heterogeneous. And not only in the scanning, it's heterogeneous in the population that's recruited in the diagnostic criteria. And the question that we asked was, can autism biomarkers carry over to new sites? You would expect to have difficulties there. And the answer is, if you have enough data, and the data needed was something like 1,000 subjects, but if you have enough data, then predictions to new sites works as well as prediction to existing sites. So basically, the predictions carry over to new sites in different countries. So based on this, I don't believe that for prediction, heterogeneity is a roadblock. And there is a reason behind this, is that unlike classical statistics, multivariate predictive models can learn to reject confounds if they have example of confounding heterogeneity. And that's something that's very different from classical statistics, and so that's why intuitions that we might have do not carry over. So yes, we can extract biomarkers despite heterogeneity. So clinical outcomes. We seldom have the perfect measure that we would like to predict. So for instance, we might be interested in predicting brain aging because, for instance, given the lack of sleep, my brain might be aging very fast currently. And that is different from the chronological age. So with Franz Liem a few years ago, we looked at predicting the aged, but based on the chronological age, based on the date of birth of people. And so, we built a machine learning model, and we predicted age with an error of 4 years. Now, the interesting thing is that the discrepancy in the prediction for our predicted brain age with the chronological age correlates with cognitive impairment. So why do I think this is interesting? I think this is a good example of a proxy clinical outcome. We don't really have the clinical outcome that we're interested in. However, a good predictive model based on what we have is a surrogate but useful biomarker. So I believe in surrogate biomarkers. We should describe subjects better. We can't really, reduce an individual to a single diagnostic or behavioral quantity. But once again, this is a problem that can be tackled with machine learning if we do multiple output prediction. And so a few years ago, we looked at predicting jointly multiple individual behaviors. So the prediction target being both the behavioral score and the diagnostic status. And the interesting thing was that predicting them together improve the prediction. So adding MMSE as a target for prediction, not as a feature to predict from, would improve Alzheimer's disease prediction. Basically, the models can learn the shared variance between those measures. So if we want trustworthy biomarkers, they need to generalize to new sites, to new subjects. Whereas bad biomarkers, on the other hand, they will overly adapt to few subjects or to site-specific observation noise. So this is a typical problem of predictive modeling. In other words, machine learning. So we need to focus on prediction rather than association, on out-of-sample statistics. And one does not simply claim prediction. One is to show it, and prediction requires more than association. So here I'm just looking at, I'm just looking at model fit, and I can fit a line in this bunch of points. I can fit a more complicated curve. And here, the red one is the curve that fits the data best. So if I was going to look at association, this red curve would be the one that is most associated with the data. However, maybe with this simple figure, you won't claim that this is you won't believe my claim that this is a useful curve. And the reason being that the quality of fit on the data that is used to fit is not meaningful. That's something that's well known to machine learning because we in machine learning fit complex models. But that's something that is not common in classical statistics because we fit simple models. And so the point being that only test data can measure prediction. So this is classically established by cross-validation, right? You split the data in subparts, you train the model on part of the data, and then you test on the other part. However, if you look at publications that have in their title or abstract fMRI prediction, the majority does not do cross-validation at all. This is work by Grace Hunkins and Russ Poldrack with myself. Grace surveyed the literature manually. So is cross-validation solid evidence? Well, this curve is showing you the reported prediction accuracy as a function of the sample size of a study in the literature. And it's showing you that in the literature, the effect sizes tend to decrease with the sample sizes. Why is that? I believe the reason is that when you have a small sample size and you vary different aspects of the analytical pipeline, you're just going to sample noise because with a small sample size, your observed prediction accuracy will vary a lot because you don't have enough subjects to measure well the prediction accuracy. So this is a small experiment I did on data where I had shuffled labels. So there was absolutely no information in this data. And what you can see is that I'm varying different aspects of the decoders, and I'm getting hugely different answers. And on the top of the figure, you see when I have less data. When I have less data, the answers vary more than when I have more data. So the thing is that with a small number of subjects, by chance, some analytic choices seem to give good prediction, but it's just by chance, right? Now, if I take the topmost of these, I'm reporting an excellent prediction accuracy, even though there's nothing in my data. This, by the way, is very well understood. This can be modeled as sampling noise from a binomial distribution, if you want to put math onto this. And the problem is that sampling noise from a binomial distribution is very large with a small number of data points, and it decreases, but only slowly with a larger number of data points. So the point being that with a small number of samples, cross-validation is not solid evidence, and this is found, for instance, if you look at the difference between subsets of data in publications. So the point being that one does not simply claim prediction. For this, we need clean cross-validation. Ideally, we would want strong generalization by testing on data that we've never seen, and we would need at least several hundreds of subjects, maybe several thousands of subjects. So, to conclude this part, I believe that reliable prediction of clinical endpoints would be game-changing, but we need larger sample sizes, we need reduced analytical variability, and we need clean validation. And I wanted to talk about how we try to reduce the analytical variability, because that's a study that we did in our lab last year, comparing many different pipelines on different cohorts with 2,000 individuals to try to get reliable answers of what is important to build resting state biomarkers. But I'm running out of time because I thought that the main messages were more important, so I'm just going to skip to the conclusion. So I'm just skipping those slides. There we go. So maybe I'll do it the other way around. So biomarkers can be game-changing if they're trustworthy, and the recipe, you can read the paper if you're interested in, but the recipe that we found was that for this, and we benchmarked this on many subjects to have a reliable conclusion, but for this we need functional regions extracted by IC or dictionary learning. We need a tool that's called tangent space to compare connectomes, and then we need simple linear models for supervised learning if we want trustworthy methods. And I claim also they would be game-changing because they could be useful for many clinical applications if we could really trust them, for instance, for early assessment, for prognosis, or for clinical, for proxy clinical endpoints. But I claim that we are failing because they're not reliable enough, because we're not setting the goals high enough. We need larger sample sizes. We need clean evidence of generalization. And for this to achieve, to meet the clinician needs, basically, I believe that we, as a community, including me, need more vision and higher standards. Thank you.